Today we'll be looking at linear models. Our objectives for today will be to identify exact and approximate models, to write a linear function from a table, to write a linear function from a graph, and to write a linear function that models a real-life situation. So let's begin by looking at exact and approximate models. I want to give you two graphs here, and I want you to tell me what you notice that is different about the two of them. Well, hopefully the one on the left you say, well, gosh, the little red line goes through all of the little blue dots. And on the right you say, well, you know, the red line gets close to it, but it doesn't actually hit all of the blue dots. Well, that's because on the left what we have is an exact model, and on the right what we have is an approximate model. Now hopefully that's not a big deal and you go, well, I get that, so let's keep going. Next, I have a question for you. I've got a table of data here, and we want to know whether or not this function is an exact or an approximate model for that data. Well, how in the world could we determine that? Well, what we want to do is we want to take each of these x values, the 5, the 10, the 15, and the 20, and we're going to plug those in. If we get out, when we plug in a 5, if we get out a 0, and if we get out a -1 when we do the 10, and if we get out a -2 when we do 15, and if we get a -4 when we plug in 20, then our function is an exact model. If any one of these does not give me this y value, then our linear function is just an approximate model. So let's start checking. First of all, we'll calculate f of 5. And by the way, we've got to deal with decimals here, and if you're uncomfortable with those, that's not a big deal. Just grab your calculator and do those multiplications if you need to. When we plug in 5, we should get 1 minus 1, or 0. So let me ask you, when we look at this first piece of data here, up to this point, could this still be an exact model? And the answer is yes. We plugged in a 5, we got out a 0. So let's look at our next set of data. When we plug in a 10, we get 1 minus 0.2 times 10, 1 minus 2, or a -1. Once again, I hope you see that right here when we plugged in a 10, we got out a -1. So once again, so far this still could be an exact model. Let's continue with 15 now. When we plug in the 15, we get 1 minus 0.2 times 15, or 1 minus 3, for a -2. Once again, you see that when we plugged in a 15, we got out a -2. This still could be an exact model. It is not sufficient at this point to stop and tell me that it is exact, because we still don't know about every ordered pair of numbers. So let's now look at the last one. We have f of 20 is equal to 1 minus 0.2 times 20, or 1 minus 4. So we get -3. Now let me ask you this question. Based on what you see on the screen right now, is this an exact or an approximate model? Well, because this one right here did not give us a -4, we got a -3 instead, you should tell me that this is an approximate model. If any one of them is off, it is approximate. Let me ask you this question. If I made a change right here, and instead of putting a -4 there, I had the -3 in the data table, then what would you tell me? That this would be an exact model. So I hope you understand the difference between exact and approximate models. What we want to do now is we want to write a linear function from a table of data. That means I'm going to give you a set of data, and your task this time is to be able to write a linear function. Now, it is not sufficient to tell me that the data is linear. We'll look at that first, but we also have to be able this time to write the linear function. Well, before we go any further, let's examine whether or not the data is even linear to begin with. You should remember how to do this. Let's look at it and see. When we start here, we move 2 units this way, and we have 4 here. Let me write those in, 2 and 4. Again, we have 2 units and 4 units. So far, this still could be a linear function. Let's go one more. From here to here, is 1. Now if this is going to be linear, we can't go 4 down here. What should we do instead? 2. Okay? For every 2 you get 4. You can think of it as a fraction there. And here you have the same fraction. Well, and then once again you have 1 unit and 2 units. So you'll see there that this is indeed linear data. But that's not sufficient for us to write the function. What are we going to do with that now? So let's look at what we need to do to write a linear function. Well, in order to do this, we need a slope and a y-intercept. Well, we have enough information here to calculate a slope. Remember, slope is simply y2 minus y1 divided by x2 minus x1. Well, you could calculate a slope for me then, could you not? It would be, why don't we just use these 2 points right here? So it would be 16 minus 12 over 2 minus 0, which is equal to 4 over 2, which is equal to 2. Now, by the way, guys, you should see this right here. It's just that it's upside down. This is rise over run. Rise, remember, always deals with your y values, and run deals with your x values. So you simply should have been able to skip this step right here and go to 4 divided by 2. Okay, for a slope of 2. Over here it's 2 divided by 1 for a slope of 2. But if you need to go through the whole process, this is your formula for calculating slope. Now let me get that out of our way and let's talk a little bit more about slope. Our slope, as we just said, is 4 divided by 2, which is 2 over 1, or just a 2. So now at this point I need you to understand, once you have the slope, you know the number that is going to go right there. The next thing we need to know is we need to know a y-intercept. Well, let me remind you, y-intercepts always look like this. They are a point where x is 0 and y is some number. Well, if you look at this data up here, where is the one where x is 0? Well, it's right here. So what you actually have there is a point 0, 12. Well, let me ask you a question. Is that a y-intercept? Y-intercepts always have a 0 there, so yes, indeed it is. So in this particular data set, your y-intercept is 0, 12. Now, let's focus one more time here. The 2 pieces of information we need are a slope, which we already have, and a y-intercept, which we now have. So let me ask you a question. Could you then fill in this data? This would go right there, and this would go right there. So what you would have for your linear function is f of x is equal to 2x plus 12. I do want to point out to you that you could not have used this piece of information or this piece of information for getting that y-intercept. This is the only one that gave you that because it is when x is equal to 0. Now what we want to do is we want to look at how we can write a linear function when we're given a graph. So let me give you a graph. Once again, I need you to remember that the 2 pieces of information you're going to need are a slope and a y-intercept. Well, how in the world can you get a slope when all you have is a picture? Well, let me remind you that slope is always equal to rise over run. You have the right to come over here and simply count that slope. I'm going to count from this point to the other point, and I'm going to count rise and then run. So to get from here, it's like you're riding an elevator up. It would be 1, 2, 3, 4. So my rise would be 4, and then I need to run. Well, I'm moving to the right here, 1, 2 position, so it would be rise over run. Well, that's exactly what we have here is 4 over 2, and when we simplify, we get a slope of 2. That's one of the pieces of information that we're going to need, and it's going to get plugged in right there. The next piece of information I need is a y-intercept. Well, where in the world is x equal to 0 on this graph? Well, right here is where x is equal to 0, so there's your y-intercept. It's where the line crosses the y-axis. Well, what is that point? Can you figure it out? When x is 0, what is y? -4. So 0, -4 is your y-intercept. Once you have this piece of data right here, what can we now do with it? Well, it's the piece that's going to go right there. So now you can write for me a linear function. f of x is equal to 2x minus 4. Please note that this right here is a negative number, so instead of a plus b here, you actually see a minus b. If this number is positive, then you see the plus. I want to make sure that you've got the big picture here. It's time for one of those Kodak moments. Anytime your task is to write a linear function, your starting place is to say, I need this information. If I have a slope and a y-intercept, then I can write a linear function. So that's your starting place. In the lessons coming up soon, we'll talk about what happens when we have a slope and we don't have a y-intercept. But for right now, we're always looking for a y-intercept and a slope. Now what we want to do is write a linear function that describes a given situation. So let's look at one. What if I ask you to write a linear function that describes the number of hours in a day? Well, let me ask you, how many hours are in Monday? Hopefully you're telling me 24. How many are in Thursday? Still 24? I know that some of you think you have more hours in your day and you can work full-time and take care of 4 kids and be a full-time student and love every minute of doing online algebra. But in reality, we all only have 24 hours in our day. So how can I write this as a function? f of x is equal to 24. No matter what the day is, I always get 24. By the way, this is a constant function. No matter which day I pick, the answer is always 24. It's a constant function. And by the way, it would look like this. Remember, constant functions will always be horizontal lines, and so there you see it. Let's go to our next situation. What if I ask you this time for the number of hours in x days? As in, how many hours are in 3 days, or how many hours are in 6 days? How can you write that for me in a linear function? Hopefully you're thinking, well, f of x is equal to 24 times ever how many days I have, so 24x. So let's look at the graph for this one. Let's talk a little bit about the axes here and what each one of them represent. Across the x-axis, we're actually going to be looking at the number of days. And the y-axis will represent the number of hours. So, when I have 0 days, how many hours do I have? Obviously 0 hours. What about when I have 1 day? How many hours do I have? 24. Well, what happens when I have 2 days? The number of hours goes up. What happens when I have 3 days? The number of hours goes up. And you can see here it's a linear function that's described by this picture. Let's look at another one. This time we're going to be looking at the distance a jogger is from home after X hours of jogging. If the jogger started 1 mile from home and jogged at a pace of 3 miles per hour. Let's see if we can do some reasoning on this before we start trying to write an equation. First of all, let me ask you a question. Jogger gets in his car and he drives to wherever he's going to start from, maybe to the Greenway or whatever he's going to do. And at that point, he's 1 mile from home. So now, without jogging at all, he's 1 mile from home. So when he has jogged 0 hours, he is 1 mile from home. Tell me what happens when he runs for 1 hour. He's now 1 mile that he got in the car and drove, plus 3 more miles for that hour that he jogged. Well, let me ask you, what happens when he runs 2 hours? Well, he's still that 1 mile, that initial mile that he was away from home, plus this time it's 3 times ever how many hours is that he's run. Well, what about when it's 3 hours? You should see a pattern here. The 1 hour plus 3 for every hour. So what on earth would our linear function look like? Well, it would be f of x is equal to 1 plus 3 times x, where x represents the number of hours that he jogs. Now for some of you, you may like it better if you can actually turn it around and it'll look like a linear function, and that's perfectly legal to do that, because a lot of you like to see that slope first and your y-intercept right here. I want to point out to you that this y-intercept corresponds to the initial distance he is from home. How far is he away from home when the problem starts, before he jogs the first step? And that's that initial distance right there. Now what I'd like to do is show you a graph of this situation. Before we talk about the actual graph, let's talk about the axis so that you understand which one represents what information. Across here we'll have hours, and on the y-axis we'll have miles. So let's evaluate this graph a little bit based on the information we now know. When the jogger has jogged 0 hours, how far is he from home? 1 mile. Do you see it on your graph? Now let me ask you this question. When he jogs for 1 hour, how far did you tell me he was from home? A total of 4 miles, the 3 he jogged plus the 1 initial mile, and there it is on your graph. What about when he's 2 hours from home? 1 hour plus the 6 more that he's jogged should put us up here at 7. And so you see that this graph really does represent exactly what we've talked about in this problem. Something that may help you when you look at this problem is how in the world do you know which one to put on which axis? The one that's on your x-axis is always the one that is consistently spaced, meaning hours in a day. If you're talking miles per hour, you want the hours to be on your x-axis. If you're talking miles per gallon, you want the gallons to be on your x-axis and the miles on the y-axis. The one that you're not sure what's going on with it is the y-axis. So that may help you a little bit when you try to draw these graphs. You know, as I've gotten older, I've learned that sometimes laughing our way through difficult times really can help us. I want to leave you with this quote from Bob Newhart. I know that many of you are not old enough to remember him, but some of you may be. And you may remember, this is my brother Daryl and my other brother Daryl. If you're not, ask your mom and dad maybe. But here's a quote from Bob Newhart. Laughter gives us distance. It allows us to step back from an event, deal with it, and then move on. I hope you can laugh your way through this algebra class a little bit with me. I'll see you soon. Bye-bye.